Okay, hello everybody. In this short video, we're just going to go over the last MPI assignment that we will do this semester for ITCS 3145 Fall 2023. In this assignment, we're going to do a relatively simple MPI application because we don't have time to do a more advanced one. Although we will do some more advanced ones in class to give some more perspective on how this is useful. But for this problem, it's relatively straightforward. So you're asked to parallelize a matrix vector multiplication using MPI. And so in this assignment, you'll be given code that runs it sequentially, and your goal is to use MPI to distribute it. In this case, it says you should distribute rows to each process. I'll show you what that means in a minute if it's not clear. And your implementation should account for cases where there are more rows than workers, which means each worker should get more than one row. And I think that's going to make a lot of sense because there's no point in parallelizing this if it's not big enough to make it worth parallelizing. And again, you should use MPI collectives where possible. In this one, I think you can get away with only using MPI collectives. That means you don't need to use MPI send and receive. You really want to focus on the collectives because that's what sets this assignment apart from the previous one. So basically, you're going to do that. You're going to parallelize the code. You're going to make sure it works for when there's more rows than workers. You're going to make sure it still produces the correct result. And when it's done, you can include a README file that explains how you parallelized it briefly and reports your speed up for this use case, which is certain problem size and how many nodes and how many iterations. So before we go over the actual problem, let's just take a look at what we're given. So we're given two files, this make file and this Matvec. You may have to change the make file a little bit because, of course, we're doing MPI. And you'll really want to make sure you're on Centaurus whenever, at least when you're compiling and running your code to make sure that everything works correctly. So this is the code we're given. So if we check it out real quick, we see we need 3 arguments. One is the problem size, one is the number of iterations. Of course, the other one is the name of the file, which is a default argument that you don't have to, or I guess you've always typed in explicitly. Okay, and then we're going to extract our problem size, our number of iterations, and it's going to do a bunch of work to set up this matrix vector multiplication for you. And we can see it's actually already set up to benchmark as well. So we'll be able to see how fast the code is. Now there's some handy comments here that say, okay, basically all your changes take place between these two blocks. And that's true. You should really focus here. I don't think you want to overcomplicate this. What this code does is it performs, for every iteration requested in the command line arguments, a matrix vector multiplication. And we can infer from here that we have a few, after each iteration, we're going to have to perform a swap, a quick swap between X and Y. And I'll show you what X and Y are here in a minute. But often, matrix vector multiplication is written as A times X equals Y, which means that if we're going to do this iteration multiple times, we probably need to swap Y and X around to get us some more useful result. And this is pretty common for a lot of types of iterative solvers, basically programs that try to solve the state of some larger problem that can't be solved explicitly. What that means is there's no absolute equation you can write down to get the solution. We just have to run the code. And we can, once we run the code, we'll get a solution. We can estimate how close that solution is to the real solution. And then we run the code again until it's close enough that we're happy with it. This is relatively common. Again, I call it solvers. There are certain types of systems of equations that you just can't solve directly. or it would be incredibly expensive to try to solve it directly. And so we use this sort of iterative process. So it does make sense to do this matrix vector multiplication iteratively. You do it over and over again until you get close to the right answer. The easy thing to turn to for these cases nowadays is always machine learning, AI. Training AI has this kind of process. You have to do some matrix, in AI it's usually matrix multiplication, and you get some result out, and you continually measure the error of that result and then multiply again until you get to where you want to be. In any case, after that, we check the solution. Now, it only checks for iteration 0 in this case. It's pretty easy to adapt this to check each iteration. But generally, as long as you're only changing the MPI code, if it works on the first iteration, it works on the subsequent iterations. If you start changing the other logic, if you start changing how Matvec works, then this may not actually work. Which is good, because you're not actually supposed to change Matvec significantly. You'll notice Matvec, the code for Matvec is up here. And it doesn't really need to be changed very much. This is very similar to the vector addition problem that we did earlier. You don't need to change the code much. You just need to change how you present your solution to the code. Although you may have to make some small changes up here. It just kind of depends. In this particular case, you may consider changing in, and you'll see why in a second. You may need more than one in as an argument. This code is written clearly to do square matrix multiplication when we divide matrix vector multiplication. When we break up the problem, it's probably not going to be square anymore. So you may have to make small changes to make sure that you capture both dimensions, but otherwise the code mostly works for itself. Likewise, the check, you're welcome to change this to support multiple iterations if you want. And likewise, we have some very basic initialization functions for the A matrix and the X vector. To keep things simple, you're welcome to change these if it helps you, but of course you should change them back when you submit your code. Okay, so anyway, that's a rundown of the code. It basically calls Matvec multiple times. And Matvec is going to do a matrix vector multiplication. To explain what a matrix vector multiplication is, in case we're not sure, we should just go ahead and let's just draw it out. So let's see. So typical matrix, we can even assume it's square for now. Looks like this. You've got rows and columns, and for this problem you can assume that the input matrices will be square. Although, again, once we start breaking it up, the individual matrices you work with may not be square. So in this case, you fill this matrix with elements. It doesn't really matter what they are. Problems work with various sizes. We have initialization code to give it specific values, but of course the code doesn't really care what the values are. You just perform the multiplication. So this matrix is what we would call A, and of course the rest of the values are filled in here. And then we have a vector X. Again, it's a vector because in this case it's only one dimensional. And we're going to multiply these two things together and get an output vector Y. So matrix vector multiplication works this way. You get an output vector that is the same size as X. And so X is full of values too, and we're trying to fill in Y. So to compute the solution vector here, Y, we follow a pretty simple procedure. Basically, for every row in A, we multiply pairwise the row by the column vector X. So what that means very plainly, if you're a math head, this is a dot product, right? What that means is that if we're going to multiply these two matrices, element 0 in the output vector is going to be A00 times x0 plus A01 times x1 plus A02 times x2. So 1 times 2 plus 2 times 3 plus 4 times 4. So you end up with 1 times 2 plus 2 times 3 plus 4 times 4. You're just matching the elements to how they are. You could take this row, turn it sideways, and it would look the same, and you just multiply across. 1 times 2, 2 times 3, 4 times 4, okay? And so that's really what matrix vector multiplication does, and that's what your code here on the screen does too. Let's switch back over. For each row and each column, we do the sum, we add up the sum from x at whatever your column index is, so we iterate through each column index, and then row times in plus col. What this means is row, like the number row, the index of the row you're on, row 0, 1, 2, times in, which is the width, it's how many columns you have, plus col, which is which column you happen to be on right now. So what that means for us then is that when we're doing row 0, you do 0 times n plus the column, and that gives us the index of A. If we were doing row times n plus column with a row 1, that means row times width. So since width is 3, 1, 2, 3, oh, that just puts us at the start of the next row. So this is using a one-dimensional array as if it was a two-dimensional array and just computing the offsets. So that's why A is still a matrix here. So we can take a look back at our whiteboard. So it's simple. You just break each vector off, you multiply it against this static vector that we're going to use for every multiplication, and that gives you an output. So in this case, your output would be what? 16 plus 6 plus 2. So you end up with 24, and that's your result here. To do the next one, you would do 2 times 2 plus 5 times 3 plus, we don't really know what this is. I guess I can pick a number, 1 times 4. And that gives you the next result. You get 4 plus 15 plus 4, which is going to be something like 23. And so that's the big idea here, is we just multiply each row by the column vector and get a single element out of it. And so this is our problem, and this is what the sequential code already does. Your goal is that for a very large matrix that has many rows, many more than I'm even able to draw here, we want to break up the problem so we can multiply them in parallel. You'll notice each one of the outputs here has no dependency on any of the other rows. So we don't, and really each output here has no dependency on any other output. So we can compute each output here in parallel. So what that means then is we can go ahead and parallelize it. So our goal here, let's say for example we have 2 workers, is to cut the matrix in half and have the first half compute the solutions, and the first worker compute the first half of the solutions, the second worker compute the second half of the solutions. Our first example isn't great for that, but if we have 3 workers, then 1 worker could do row 0, 1 worker could do row 1, 1 worker could do row 2. and we could do them all in parallel and we'd get the correct solution. So that's what we're moving for. The key idea being, though, that we want to partition the matrix to fit for our number of workers. This matrix, if we have 2 workers, clearly each worker needs to do more than 1 row. So why not just give the first worker half of the matrix and the second worker half of the matrix? And so that's your goal here, is split the matrix up into pieces and have each worker do parts of it. So the challenge here then is, how do I map this to being an MPI problem? And that's what I am leaving you to figure out. You might consider that there are MPI collectives that enable you to do things like break up a matrix into equal-sized pieces. And you can assume for this problem that it's equal sizes and we don't have any issues with that. You might also consider, we really need this vector to be on every node because every node needs this vector. Maybe we have a way to communicate one piece of data to every vector. And then finally, we do need to get our solution back together. Every vector, every rank is going to have its own partial vector. Maybe we have a way to put data back together once it's been broken up into pieces. So consider those tips when you're working your way through this. And yeah, overall, that's really the summary here. So with that in mind, take a shot at it. And if you have any questions, please reach out to us and we will try to answer them as quickly as we can. Or come to group study or office hours or these sorts of things. All right, we'll see you next time.